Okay, so this will be the first of a couple of lectures that we're going to have that are meant to review topics that we've covered over the course of a week. We've done a fair amount of stuff already, and I think one of the things that people might be having difficulty with would be hybridization. So I'm going to go ahead and just give a quick review, maybe 30 minutes or so, on hybridization. So we are interested, of course, really in hybridization of the elements principally in the second period. So we're interested in SPN hybridization, where n can be 1 technically, or you wouldn't write the 1, or it can be 2 or 3. And this would include elements like carbon and nitrogen and oxygen principally, or it could include elements in the third period or beyond. Windows journal is messing up here. That's weird. Okay, so hybridization then. So carbon in its ground state is 1s2, 2s2, 2px1, 2py1, and because we'll be using a 2pz orbital in a little while, I'm going to write 2pz0. And this represents the ground state, right, of carbon. In other words, this is the electronic configuration that you would write based upon the off-war principle, the Pauli exclusion principle, and Hund's rule. And carbon, of course, is element number 6. So there's 6 protons and therefore 6 electrons. Both 2 electrons will occupy the 1s orbital, 2 will occupy the 2s, and 1 each singly with the same spin in the 2px and 2py. We saw that this configuration is not the one carbon uses to bond. It cannot be because it would account for only divalence in carbon, and maybe at a stretch trivalence if you were to use the 2s2 electrons. So carbon would form 2 ordinary covalent bonds via the p orbitals, and then 1 dative bond via the sp2. But if it did that, it would only be trivalent and the species would be positive. And in any event, the characters of the bonds are very, very different from what you actually observe. So we realized very early on that what carbon did is that it promoted one of the 2s electrons and became 2s1, 2px1, 2py1, and 2pz0, 2pz1. And we call this the excited state of carbon because it's clearly a higher energy state. It's not the stable configuration. And we talked about it in class that what essentially we're doing is we're putting in 2 quanta of energy, because we're moving from a scenario where we have 2 electrons in the 1s, 2 in the 2s, and 1 in each of the 2p's. We're going to a scenario where we have obviously the same 2 in the 1s because those are core electrons, and therefore we don't interfere with those, not at least in chemistry. And this time we're going to take one of the 2s electrons and promote it into the 2pz. And so this is the excited state of carbon. And while that excited state could account for the tetravalence of carbon, because I have 4 unpaired electrons, right, 1, 2, 3, 4, it does not account for the shape, for example, in methane. It does not account for the shape in ethene or in the alkyne. It doesn't account for a bunch of other properties like the equivalence of all the CH bonds in methane and so on and so on and so on. But this excited state is, I guess, what you might call the active configuration from which carbon hybridizes. Now, the choice of hybridization state depends upon what the carbon is doing, and ultimately comes down to the question, how many pi bonds is the carbon forming? Because the thing is, if I'm going to form a pi bond, right, there's certain rules about bonds, right? We said all single bonds, right, all single bonds are sigma bonds, okay? And we talked about that last time, that it's better for an atom to form a sigma bond because, and the ideal example would be fluorine. Fluorine bonds via its p orbitals, and if the fluorine atoms came together in an end-on fashion to form a sigma bonds. I'm going to give them phases now. So let's say plus and minus and minus and plus. So this is a homophasic interaction. Again, these minuses and pluses do not indicate charges, right? These just indicate phases. So I could have put shaded and blank or whatever. What this gives rise to is a fluorine-fluorine sigma bond that essentially looks like this, right? There'll be a little vestigial lobe here, a little vestigial lobe here, and these would be plus, this whole thing would be minus, and this would be a plus as well. And this represents the sigma orbital of a fluorine-fluorine bond. Occupation of this molecular orbital would give rise to bonding between F and F. But the bulk of the electron density is positioned between two fluorine nuclei, and as a result we minimize repulsion and we actually maximize attraction because the electrons are very close to the nuclei. But on the other hand, if the fluorine chose to bond in this fashion, in other words, orient the p orbitals so we could only do side-on overlap, right? And again, if I were to put in the phases, it would be plus and plus and minus and minus. What we would get from this would be a fluorine-fluorine bond that would look like this, right? I'd have a swell of electron density here. Well, this is drawn rather badly, but you get the point, all right? And this would be plus, and that would be minus. But in this scenario, I expose the fluorine nucleus to another fluorine nucleus, so there's massive repulsion. And the swell of electron density is actually pretty far from the nuclei, and therefore the force of attraction is not great. So all single bonds are going to be sigma. So that's one of our abiding rules. The other rule is that all pi bonds, right, all pi bonds arise from side-on, right, from side-on or collateral overlap of p orbitals. Okay, and this becomes very important in our discussion of hybridization state. So all pi bonds are formed from the side-on overlap of pp orbitals. And then finally, in a multiple bond, in multiple bonds, right, only one is sigma. So if I have a carbon-carbon triple bond, for example, then one of them is sigma, and we don't know which, it doesn't matter whether I put the bottom one or not, and therefore in that case, these two would both be pi. Right? Or if I had a C double bond O, then one of these, let's say this one is sigma, therefore this one has to be pi. And since these bonds are single bonds, these would have to be sigma bonds themselves. Okay? So why is this important then? If in the second point we said all carbon-carbon pi bonds, or all pi bonds are formed by pp overlap, when my carbon, which begins as 1s2, 2s1, 2px1, 2py1, 2pz1, if the carbon is going to form a pi bond, it's going to form one pi bond, then it must reserve one p orbital for pi bond formation, because all pi bonds arise from side-on pp overlap. So if the carbon is going to form a pi bond, it must keep one p orbital to form the pi bond, in which case it will hybridize the 2s with the remaining p orbitals and become sp2 hybridized. On the other hand, if the carbon is going to form two pi bonds, as for example in the case of the alkyne, right, then that is going to have to keep two p orbitals reserved for pi bond formation. It'll keep these two for pi bond formation, hybridize the rest, and become sp hybridized. If the carbon is forming no pi bonds, well then it doesn't need to leave any unhybridized. It'll hybridize them all and become sp3 hybridized. So let's go in a series then. Let's say we're forming no pi bonds. Right? So forming no pi bonds. In other words, let's say the compound we're going to be forming is, say, in fact, let's just pick a molecule of this type. So let's just say the compound we're forming is this one. Right? Well, if I'm interested, for example, in this carbon, right? If I'm interested in that carbon, oh, stop it. If I'm interested in this carbon, then I can look and say, well, this carbon is forming a single bond here, a single bond here. It's a bond line formula. So it's understood there's single bonds to two H's. So there are no pi bonds whatsoever. In which case, this carbon is going to hybridize the S with all three P's, because I need not reserve any p orbital for pi bond formation. So what we'll do is we'll take our 2s1, our 2px1, our 2py1, our 2pz1, and mix them all. All get mixed, right? I toss in 1 can of red, 3 cans of white, and I get from this four separate 2sp3 hybrids. So I get 4 sp3 hybrids, and they're all going to be from the second quantum level, and the carbon therefore is going to be sp3 hybridized. Well, what if the carbon was forming a compound of this type, right? What if it's going to form one pi bond, right? Let's say instead we're looking at this compound, and I'm interested in the hybridization state of that carbon. Well, this carbon is clearly forming one pi bond, therefore it must reserve one p orbital for pi bond formation. So it's going to take the same basis set, 2s1, 2px1, 2py1, 2pz1, and it's going to say, you know what, this is untouchable. I must leave this alone in order to form the pp pi bond with the other carbon. So what do I have left? And the answer is, what you have left to hybridize would be these. And so I'm going to toss into a pot 1 part red, 2 parts white, okay, and I'm going to end up therefore with 3 sp2 hybrids, okay, and each of those hybrids will contain 1 electron, okay. Well, what if the carbon is going to form 2 pi bonds? In other words, if we're looking at a compound of the type, say, C triple bond N, right, like an 8CN, or maybe we're looking at, say, the carbon in carbon dioxide, right? In both of those compounds, the carbon is forming 2 pi bonds, 1, 2, or 1, 2. Well, in that case, it's going to take the same basis set, which is the 2s1, the 2px1, 2py1, 2pz1. It's going to say these 2 p orbitals must be left untouched, because I need to dedicate those to forming the 2 pi bonds. In which case, what I have left, I can hybridize, which will be the 2s and the 2p. So I'm going to toss in a pot 1 part red, 1 part white. I'm only going to get 2 orbitals out, and they will both have 50% s character, 50% p character. So I'm going to get 2 2sp hybrids. And as I said, there's a superscript 1 that's understood both here and here, meaning it's 1 part S, 1 part P, right? 1 part S, 1 part P. In the same way with my sp3s, it's understood it's 1 part S, 3 parts P, 1 part S, 1, 2, 3 parts P. So all I need to do to decide what is my hybridization state is to look at the carbon and ask this question: how many pi bonds, if any, is my carbon forming? And if the answer is no pi bonds, because I have to have in my head what are my basis set, what is my basis set of orbitals, and that would be the sp, that would be the s, the px, the py, the pz. And if I'm forming no pi bonds, I'm going to hybridize everybody, because remember, hybridization is to my advantage. And the reason hybridization is to my advantage is because I am lending every orbital s character. And if I give every orbital s character, right, then every orbital gets shorter, which means the bonds that they form are shorter and therefore stronger. I release more energy. So it's to an atom's advantage, by and large, to hybridize. And unless somebody tells it you must dedicate an orbital for pi bonding, you must dedicate a p orbital to form a pi bond, it will hybridize the s with every available p. Okay? So let's say, for example, I gave you this question. I can't find my cursor. Okay, let's go here. Let's say I gave you this compound, and I said, let's identify the hybridization states of, whoa, that doesn't look very good. Let's identify the hybridization states of the different atoms in this compound. So let's have put an oxygen here, maybe put a carbon oxygen double bond, put a nitrogen on here, put a lone pair, maybe put a C triple bond N, C triple bond P perhaps, with a lone pair on it, put a double bond here, I'm going to put another nitrogen here, with 2 H's and a lone pair. So if I were to finish the Lewis structures, which I know you guys are expert at now, there will be 2 lone pairs on each of those, right? And so let's say my question is, what are the hybridization states of the carbons in, well, in fact, let's do them all. So let's take a fluorine on this atom, or let's say a bromine, because we've talked about fluorine in class, right? So my question is, what are the hybridization states of the atoms I'm going to flag? So I want 1, the hybridization states, and some people simply say, what are the hybridizations, right? Which is perfectly fine, potato, potato. And 2, if they have lone pairs, I want to know in what orbital or orbitals are the lone pairs of electrons housed. And I also want to know what is the character of the bonds. So I'm going to look at bonds, and I want to know what type they are, in other words, sigma or pi. And I want to know the constituent orbitals. In other words, what orbitals are used to form those bonds. So that's basically what we'll be looking at. So let's start, for example, with H. Right, let's call this A. Let's call this B. Let's call this C. Let's call this one D. Let's call this one E. Let's call this one F, G, and H. So I want to know for A through H, what are the hybridizations, and in what orbital are the lone pairs housed, if there are any lone pairs. So A, so I'm looking at hybridizations. And orbitals housing my non-bonded electrons, or my lone pairs of electrons. You know what? Let's do that N as well. So we reached E. Oh, idiot! Now this is E. I'll make this one. So I'll make this one F. Make this one G, make this one H, make this one I. So we're looking at A, B, C, D, E, F, G's. G, H, do I have room left? Nope, no more room. Bummer. Okay, I'm just going to have to make some more, be a bit more elegant here, so be a bit crowded. So the A, B, C, D, E, F, G, H, and I. So what is the hybridization state of A? Well, A is hydrogen. Hydrogen, because it is a first row element, has access to the 1s orbital. The 2s energy gap is too big, and therefore H simply cannot hybridize, because for orbitals to hybridize, they must have what we call complementarity. There must be an overlap, there must be good fit between the orbitals, meaning that the energies have to be similar, which these are absolutely not. In fact, the biggest gap in energy levels, in adjacent energy levels, is between 1 and 2. So the 1s orbital has no business overlapping with anything in the second row or beyond, second level or beyond, because the energy gap is too big. So the energy gap and the size gap is too big for the orbitals in the 1s level to overlap with anything else. So H simply cannot hybridize. So what is the hybridization state of the H? And the answer is it doesn't have one, right? It does not have a hybridization state because it's not mixed. Well, there are no lone pairs of electrons on the H, so that doesn't really apply, so we just put a dash line. What about the B? Well, N is forming no pi bonds, because that's the question I have to ask. How many pi bonds are we forming? N is forming no pi bonds, and therefore N does not need to reserve any p orbitals to form pi bonds. In which case, N will simply have the s, 2s, and the 3 p orbitals all merge. Because understand, if we're looking at sp hybridization, it doesn't matter what the element is, in which period the element is, all that's irrelevant, because the basis set remains S and the 3 P's. So since N, so whatever applies to carbon applies to N, to O, to F, to P, to whatever else is. So N forming no pi bonds, and I'm going to write down my set again. It'll be 2S, 2px, 2py, 2pz. So N forming no pi bonds is going to be able to hybridize all 3 P's with the S, and therefore be sp3 hybridized. Well, if the N is sp3 hybridized, then it stands to reason that my 4 sp3 hybrids are going to be used as follows. 1 will be used to form the NH bond here. 1 will be used to form the NH bond here. That's 2. 1 will be used to form the NH bond here. That's 3. And the 4th orbital, it would be the one that houses the lone pair. So, in general, if I know the hybridization state of the atom, if that atom houses lone pairs, I also know the orbital that houses the lone pairs. It's exactly the same as the hybridization state, and it must be. So if my N is sp3 hybridized, then the lone pair which it has is being housed in an sp3 hybrid. It's a little more satisfying if you can sort of pinpoint where the electrons are actually going. So for example, for nitrogen, which is element number 7, we're actually looking at 2s2, 2px1, 2py1, 2pz1. If we're saying that N is sp3 hybridized, then we're going to become 2sp3, 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 and 2sp3. In other words, I put in 1 can of red, 3 cans of white, I get 4 cans of pink. In those 4 orbitals, there was a total of 2, 3, 4, 5 electrons. So they go 1, 2, 3, 4, and then they double up 5 as in Hans rule. So this sp3, let's say, was used to form this bond. So in other words, this sp3 would have overlapped with the s of a hydrogen. This sp3 would have overlapped with the s of a hydrogen. This sp3 would have overlapped, as it turns out, with the sp2 of this carbon, and the lone pair is being housed in my sp3 hybrid. Okay? What about the atom number 3? Atom number 3 is a carbon, and I'm going to ask the question, how many pi bonds is the carbon forming? The answer is 1, which means I must dedicate one, where's my cursor? I must dedicate one of these p orbitals to form a pi bond, so I can go ahead and mix the remaining 2 with the s. So that's going to be sp2, let's write it here, sp2 hybridized. It has no lone pairs, so this question doesn't apply to us. What about D, which is the oxygen? Fundamental question. How many pi bonds is the O forming? The answer is none. Therefore, the O can merrily go ahead and hybridize all 3 P's, because it's not reserving any. It can hybridize all 3 P's with the S, and therefore that O will be sp3 hybridized. Now, the O has 2 lone pairs. Where are they housed? Now, I know the answer has to be in sp3 hybrids, because whatever my hybridization state, that is the character of the orbital housing the lone pairs. So I'm going to go ahead and write sp3. Right? But it's a little more satisfying if I could sort of figure out where my electrons have gone. So the oxygen is also 2s2. This time it's 2px2, 2py1, 2pz1. The O doesn't promote any electrons, it doesn't excite anything, because there really is no point, because any excitation will simply result in 2 unpaired electrons, right? So it's going to go ahead, as I've said, it's not forming any pi bonds, and therefore be sp3 hybridized. So I'm going to get 4 sp3 hybrids. In fact, if I'm going to get 4 sp3 hybrids, rather than just write the 4 out, I'm going to write the individual 2 sp3. So 2 sp3, 2 sp3, 2 sp3, 2 sp3. Now, I had a total of 2, 4, 5, 6 electrons. According to Hans, they'll go 1, 2, 3, 4 with the same spins, then double up. 5, double up, 6. So this sp3 hybrid is used to form a bond to say that carbon, it's sp3. This sp3 hybrid is used to form a bond to that carbon, so that's sp2. So the two remaining electron pairs now are being housed in sp3 hybrids. So this lone pair is being housed in an sp3 hybrid, that lone pair is being housed in an sp3 hybrid. And it really is very simple. If you know the hybridization state of the atom, which is a simple question to ask, how many pi orbitals, how many pi bonds do I form? If I know the hybridization state, then I know the orbital that houses any lone pairs. Okay? So I'm going to go ahead and erase this one too. Okay. I'm checking my time to make sure I don't run over. I've got some time left. And then element number or atom number or letter E. The O is forming one pi bond. Therefore, it must reserve one p orbital for pi bond formation. It'll hybridize the rest. And that O is sp2 hybridized. This is E. It will be sp2 hybridized. It has two lone pairs. So pray tell where are those lone pairs being housed? No brainer, it's being housed in the sp2 hybrids. Right? It's being housed in the sp2 hybrids. I'm just going to do it one more time just to see where it goes. So again, my oxygen was 2s2, 2px2, 2py1, 2pz1. It's going to be sp hybridized. So I'm going to leave one p, so it's going to be 2pz1, that's reserved. I'll hybridize the remaining 2 p's with my s, and I get 3 sp2 hybrids. sp2, 2 sp2, 2 sp2, 2 sp2. Now, in my 3 orbitals that I've hybridized, there was a total of 2, 4, 5 electrons. So I'm going to have 1, 2, 3, double up, 4, 5. So what does the oxygen do? It uses the 2pz orbital to form one bond, that's the pi bond, which is going to form with the p orbital of that carbon. It uses the sp2 hybrid to form the sigma bond with the carbon, also with the carbon's sp2. So I have pp to form the pi, sp2 sp2 to form the sigma. Then there are 2 sp2s, each housing 2 electrons. This is one sp2 with a lone pair, that's the other sp2 with a lone pair. And it's very satisfying to be able to identify exactly where my electrons are being housed and in what orbital they're being housed, which ones are being used to form which bonds, and so on. Okay, so I'm just going to run through the rest. Element number letter F, the nitrogen. How many pi bonds is it forming? None. Therefore, that F is sp3 hybridized. There's a lone pair on it. Therefore, it's being housed in an sp3 hybrid. G. Well, halogens prefer not to hybridize, especially when they're bound to heteroatoms. And therefore, the bromine, which also has access to the 2s and the 2p's, but this is going to be bromine. These would be the 5 fluorine, fluorine, bromine. This would be the 3s, 3p. So bromine would have, bromine would be 3s, 2, 3px, 2, 3py2, 3pz1. The bromine will not hybridize. No, is it 3 fluorine? This would be 4, I'm sorry, the 4th quantum level. So these are 4, 4, 4, 4. 3 would be chlorine. So bromine will not hybridize. Therefore, it will use a 2pz to form the sigma bond. Okay? Now remember, a sigma bond, a p orbital can form a sigma bond. Sigma does not mean I can't use p. In other words, p orbitals can either form pi bonds if they overlap side-on, or they can very easily form sigma bonds if they overlap end-on. So it's not true that p orbitals are doomed to form pi bonds. Okay? So the remaining lone pairs of electrons on the bromine, 2 of them are in p orbitals, 1 of them is in an s. And I don't know which pair is where. I just know that 2 pairs are in p's and 1 pair is in an s, and that's the best I can do. So hybridization for the bromine, the answer is none. It's not hybridized. And where are the orbitals being housed? They're being housed in a 4s orbital and in 2 4p orbitals. GH. How many pi bonds is the carbon forming? 2. Therefore, it's going to keep 2 orbitals reserved, 2p orbitals reserved for pi bond formation. It'll therefore be sp hybridized. So I'm going to write sp. There are no lone pairs in that carbon, so that's not an issue. The phosphorus, how many pi bonds is it forming? The answer is 2. Therefore, it must also be sp hybridized. And of course, phosphorus, which is a third row element, will have the 3s, 2, 3p x, 1, 3py, 1, 3pz, 1. Because phosphorus is just below nitrogen in the periodic table. So nitrogen was 2s2, 2px1, 2py1, 2pz1. With phosphorus, you just put a 3. And it's sp hybridized, so it's going to reserve these 2 for pi bond formation. It'll mix that lot together and it will be sp hybridized. So I'm just going to very quickly do this one. It'll be 3sp, 3sp, and then 3py1 untouched, 3pz1 untouched. These 3 electrons that were in the 3s and the 3p orbitals will go 1, 2, and then double up. So the phosphorus will use, I can't find my cursor, the phosphorus will use one of the p's to form this pi bond, let's say, the other p to form that pi bond, and the sp to form the sigma bond by overlapping with the sp of the carbon. There will be a lone pair housed in a 3sp2 hybrid. So I, in a 3sp hybrid, so I, which is sp hybridized, is going to have the lone pair housed in an sp hybrid. Okay, that's that. So if I were to ask a question about the bonds, right, so let's go to the next page, and this will be the last thing we do. I don't remember the molecule, which is a little bit inconvenient. Let's see, what do we look like? So, you know, I think it'll allow you to copy. Let's see. Let's say copy, and then what about if I did paste? That work? Paste. Oh, technology, man! You just can't beat it. Okay, so there's something is missing. This had a there was a nitrogen here, and then 2 H's, and there was a lone here. So let's point to bonds this time. So I'm going to call this bond 1. Let's call this bond 2. Let's call this one bond 3. Bond 4. Just random now. Bond 5. Bond 6. I'll have to call this one bond 7. What was here? Bromine. Let's call this one bond 8. Let's call this one bond 9. And that's enough. So, well, I guess let's do these then. Bonds 10 and bonds 11 and 12. So this would be 11 and this would be clumsy. This would be 12. So I'm asking, so we won't have enough room now. So let's say we don't have enough room here. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm going to ask the type of bond, sigma pi, and I'm going to ask the constituent orbitals, which I will not have room to write. So I'm going to say, put in 2 lines, so constituent orbitals. In other words, what orbitals make up the bond? What orbitals are used to form the bond? So, bond 1 is a single bond. All single bonds are sigma, right? So, if that's a single bond, then bond 1 is sigma. What orbitals are used to form it? The N is sp3 hybridized. The H is not hybridized, so we're using its S. So it's going to be the S of H overlapping with the sp3 of nitrogen. Bond 2, single bond, therefore it's going to be sigma. What orbitals? Well, the carbon is sp2 hybridized, so we're using the sp2 of carbon with the sp3 of nitrogen. Now, these are going to be a little bit, because I'm crushed for space here, well, if I were clever, what I'd have done is set up 2 tables. Uh-oh, why is this not using? Okay, so let's not be crushed for space, shall we? So let's not be crushed for space. So this is 1. Stop it. This is 1. This will be 2, 3, 4, 5, 6. So bond number 2, we said is going to be sigma. The orbitals are going to be sp3 of nitrogen and sp2 of carbon. Bond number 3. Now 3 and 4 are a double bond, and I don't care which one is sigma, which one is pi. But if I say 3, for example, is sigma, then I've designated 4 as pi, right? So the sigma bond would be formed by the sp2 of carbon, right? Let's say that carbon, with the sp2 of another carbon. And even though it's the same type, I must indicate both. Well, 4 is pi, so pi is simply p, p. It's p of carbon, p of carbon. 5 is a sigma bond. All sigma bonds are sigma. So 5, I can't find my cursor again. 5 is sigma, and 5 involves the sp3 of this carbon with the sp3 of that oxygen. So it's sp3 of carbon with the sp3 of oxygen. 6, again, 6, 7 is a double bond. So let's say 6 happens to be the pi bond, in which case it's going to be p overlap. P of oxygen, P of carbon. So that leaves us then with that's what, 6. So this is 7, 8, 9, 10, 11, 12. And this would be the type of bond and the constituent orbitals. Okay, and just checking my time here. Okay, this will be the last thing we do. So 7, what do we go with 7? So we said 6 was pi, therefore 7 has to be sigma. This will be sigma, and 7 is made up of the sp2 of carbon and the sp2 of O, because these are both sp2 hybridized, right? So the sp2 of carbon and the sp2 of oxygen. 8. Well, remember we said the halogens do not hybridize, especially when they're bound to heteroatoms. And so this will be, of course, it's a single bond, so it's a sigma bond. And it'll be P of the bromine overlapping with the sp3 of nitrogen. Right, sp3 of nitrogen. That's 8. 9 is a single bond, therefore 9 is sigma. And it's between the sp3 of a nitrogen and the sp of a carbon. So sp3 of nitrogen, sp of a carbon. How do I know that? Because the N is sp3 hybridized, no pi bonds. The carbon forming 2 pi bonds is going to be sp hybridized. Now, 10, 11, and 12 are a triple bond. Let's say 10 is the sigma, because in a multiple bond, 1 is sigma, everybody else is pi. So let's make 10 the sigma. The sigma bond is being formed between the sps of a carbon and the sp of a phosphorus. So it will be the sp of carbon and the sp of phosphorus. And it has to be that way because if both are sp hybridized, because they're both forming 1 pi bond, 2 pi bonds, then they're going to use their sp hybrids to form the sigma bonds, right? And the p orbitals to form the pi bonds. So 11 and 12 are exactly the same. The bonds are both pi, and they involve p of carbon overlapping with p of phosphorus. P of carbon overlapping with p of phosphorus. Okay, and that pretty much is the type of questions we will ask on hybridization. So in general, hybridization then would be asking you to characterize the hybridization state, if any, of the atom. And remember, H cannot hybridize, the halogens choose not to, but pretty much everybody else will hybridize because there's an advantage to hybridizing. You should be able to tell me why H cannot hybridize, why the halogens do not hybridize. You should be able to tell me why every other element chooses to hybridize. And the issue is, if you hybridize, two good things happen. You infuse S character into your p orbitals, right? And now this is just for organic, but for example, you can think of, like, say, in inorganic chemistry, where you have sp3d2 hybrids, where, you know, S's are really compact, P's are bigger, D's are even bigger still. And if I lend orbitals S character, I make them smaller. If I make them smaller, I make the bonds they form shorter. If the bonds they form are shorter, then the bonds they form are going to be stronger. Therefore, when the bonds form and they dip in the Morse curve, they release more energy and the system gets more stable. So if anybody can hybridize, right, if anybody can hybridize, they by and large will, except for the halogens, which have too many lone pairs around them. By the way, the other advantage to hybridization is that when you hybridize, in general, the bond angles tend to increase. And I think we had pointed out that with carbon, in say methane, if carbon went and formed its bonds via the s orbital and the 3 p's, the 3 p's would have been at a 90-degree bond angle. Whereas when we hybridize, they're at a 109-degree bond angle. So I've gained virtually 19 degrees, which means my repulsion is now less. And to boot, my bonds are shorter and stronger. So it's a win-win situation when you hybridize. So you should be able to discuss intelligently why H cannot hybridize, why the halogens choose not to hybridize, why everybody else will hybridize with a chance. Okay, so it's pretty much time for me to go. You should also be able to, if I give you a molecule, to identify the hybridization states of all the atoms where appropriate, to be able to tell me what kinds of bonds we have, sigma or pi, and what are the constituent orbitals in the bonds. I would also be able to expect you guys to answer intelligently why all single bonds are sigma, why we never have single bonds that are pi, and why in a multiple bond only one is sigma and everybody else is pi. And also why we can't have an XY quadruple bond, because we have single, we've got double, we have triple, no quadruples. And that is pretty much the exercise. Okay, so I will put up a second lecture on, I think we finished the bond energies pretty well. I think most people are good on that. And if that's not the case, I'll put up one later on. The next one we will do will be on redox chemistry. Okay, so you guys have a good evening or good morning whenever you're looking at this stuff. I can't find my cursor again. Here we go. Alrighty, have a good evening. Bye, guys.